This is MGF 1107, Chapter 3, still Section 3. This is Part 2. Basically, what I'm going to do is go through an example problem here so you can understand how this whole Hamilton path and circuits work. Also, it's called a traveling salesman problem. And actually what individuals do inside corporations and businesses in order to figure out an efficient way to travel or move things or deliver items, things like this. All right, so this is example 1, page 825, and this is going to be a continuation problem. It says, Priya, a chief operating office for Hard Rock Cafe International. Priya lives in Orlando, Florida, and needs to visit Hard Rock Cafe restaurants in Atlanta, Georgia, Memphis, Tennessee, New Orleans, Louisiana. She would like to determine the least expensive way to visit each of these cities one time and return to her home in Orlando. To help analyze this problem, Priya searched online and found the least expensive one-way fares offered between each of the 4 cities. That's what this table is showing here. Okay, so this is showing, obviously you don't want to take it from Orlando to Orlando, but this is Atlanta to Orlando, Memphis to Orlando, New Orleans to Orlando. Then here we have Orlando to Atlanta, Atlanta, Memphis to Atlanta, New Orleans to Atlanta. And if we go down here, so see these little stars right here represent, no flights from the same city. All right. So this indicates to us how much money is expected to be spent as we go through this process. So if we want to use a Hamilton circuit, meaning that we want to visit each vertices once and only once and return home to the same place, then here's what we have here, okay? In terms of this, here's our Orlando, Atlanta, Memphis, and then New Orleans. And notice the edges that they have here. Here's the numbers. And so we have to indicate the numbers on each edge. So a flight from Orlando, Atlanta, $103. Okay. A flight from Atlanta to New Orleans, $110. And that's coming from, this chart right here. All right. And another way to represent this would be here. This is another way. Here you have Orlando, here you have Atlanta, Memphis, and New Orleans. So, they're both complete graphs because we can see that, we have 4 destinations, but each destination goes to the other 3 destinations. So see how, from Memphis there's 3 lines, from Atlanta's 3 lines, Orlando 3 lines, New Orleans 3 lines. See here, Orlando 3 lines, Atlanta 3 lines, Memphis 3 lines, and then New Orleans 3 lines. So there's different ways to represent this, okay? But again, make reference to this. In this type of problem, traveling salesman problem, we're not only concerned with the path, we're also concerned with doing the cheapest route. So now we're on page 828 in the section. And right here, it says the Hamilton circuit with the lowest associated cost is called the optimal solution. So remember, in these type of problems, that's what we're looking for. We're looking for the optimal solution, okay? It then says we will discuss 2 methods, the brute force method and the nearest neighbor method, for determining the optimal solution, okay? In both methods, we will use the term complete weighted graph. A complete weighted graph is a complete graph with the weights or numbers listed on the edges. And so that's what I was talking about before. So in terms of this, not only do we have a complete graph here, we also have the edges labeled with the cost to fly from one destination to the other. So the first method here is the brute force method, okay? And this is for a traveling salesman problem. Again, this is the type of problem where we're trying to find an optimal solution. It says to determine the optimal solution, represent the problem with a complete weighted graph. which we have right here. Second one, list all possible Hamilton circuits for this graph. Okay, so if you come over here, and this is on page 829, here are all the possible Hamilton circuits. And by going O to A to M to N to O, remember we're trying to leave Orlando and come back to Orlando. That's a characteristic of a Hamilton circuit, is once you leave a destination, you return to that destination. And so then what they've done is they've, from Orlando to Atlanta, $103, from Atlanta to Memphis, $229, so on and so forth. And then you have total cost here. Okay? This says determine the cost associated with each of these Hamilton circuits, which they have. The Hamilton circuit with the lowest cost or shortest distance is the optimal solution. So if we look at this chart right here, we can see that we have two options. We have Orlando to Atlanta to New Orleans to Memphis to Orlando, which is 545. We also have Orlando to Memphis to New Orleans to Atlanta to Orlando, which is also 545. If you look at these two optimal solutions, you'll see basically the same thing. This is ANM and this is ANM backwards. So this is called the brute force method. It requires a little more math. Requires also you finding all possible Hamilton circuits. And remember, they figured out that there was 1, 2, 3, 4, 5, 6 circuits because we used the math. We have 1, 2, 3, 4 vertices, and if we follow our particular formula for figuring out how many circuits there are, we go 4 minus 1 factorial. 3 factorial is 3 times 2 times 1, which is 6. So we knew there were 6 possible Hamilton circuits. We just had to figure them out. The second method for figuring a traveling salesman problem out is called the nearest neighbor method. And it says here, represent the problem with a complete weighted graph. Identify the starting vertex. Okay. Of all the edges attached to the starting vertex, choose the edge that is the smallest weight. This edge is generally either the shortest distance or the lowest cost. At the second vertex, choose the edge that has the smallest weight that does not lead to the vertex already visited. Continue this process and you have your traveling salesman problem. And here's an example of the nearest neighbor. In example 4 on page 87, remember the American Idol problem. Okay, and so what happened here was we're basically making the chart the same way we did with brute force. Here's the cities we got to travel in a column. Here's the ones on the top. Birmingham to Birmingham, the so-called, but Birmingham to East Rutherford, so on and so forth. So here's the cost of them. Okay. And if you'll remember from that problem, we came up with this complete graph. So now what we've done is we've gone ahead and just listed the weights of the lines. And so that's what all these numbers represent from this table. Okay? And so if we following the nearest neighbor example, we're going to start from Houston. And if I look at Houston, I have this 108 on this weighted 134, 144, 129. So I'm going with the 108. Okay? So now I'm in Seattle. And I can't come back this way. So in Seattle, this first line's 119, this one's 155, this one's 299. So I'm going to go Seattle to San Antonio. Then from San Antonio, I got 355. I can't use 119 because I've already used it. 634, 274. So I'm going to use the 274. And now I'm going to Birmingham. From Birmingham, I have 155, I have 258, and I have 324. All right, well, I can't use 155 because I can't go back to Seattle. So I have to use between 258 and 324, so I'm going 258, which is East Rutherford. From East Rutherford, I'm going to come down to the 104 because I can't use the 258. I can't use any of them. And then once I get to Memphis, from Memphis, I'm going to go into Houston. So you got to be careful as you use this nearest neighbor example, because you got to look at the fact that you don't travel back to a same vertices. Remember, the idea behind the Hamilton circuit is that you travel each vertices only once. You're not worried about the edges.